Hello, everyone. I'm audible to you all. Very good evening.
Yes, sir.
Shag, Bhaskar, Tanmay. Yes, I'll be your deep learning mentor. Good evening. Hello. Hi. Very good evening, everyone. I hope all of you guys are doing great. And from this session, we'll be starting with deep learning. We'll discuss in detail about what is deep learning, what are neural networks. In first 15 to 20 minutes, we'll discuss the intuition of it. Then I'll take you to the project. Then we are going to write the project from scratch as well. Okay. So shall we start? Okay, let's go ahead. So, before starting, let me introduce myself. My name is Ashish Jangra, those who don't know me. I'm a data science mentor at Geeks for Geeks, working from last 4.5 years here, working as a mentor as well as data scientist uh, ep- for the in-house projects, basically. Apart from that, I'm working on data, means from data science, you mean to say data analytics, machine learning, deep learning, generative AI, and currently also agentic AI. So let's start then. Now the funda is first of all we need to discuss what is deep learning. Okay, so let's start from there. What is deep learning? Do let me know in the chats. Okay, okay. What is deep learning? Be active on the chats. You might have already heard about machine learning. Okay, and let me open a flow for you so that it would be easier for you. Uh, you might have seen this flow somewhere, right? You might have seen this flow somewhere. So deep learning is a subset of machine learning, and machine learning is a subset of AI. In AI, basically we have algorithms that can make decisions, that can make intelligent moves, right? Any algorithm of your choice. But in machine learning, we have the same algorithm, means a bit different algorithm, but they are data trained algorithm. In machine learning algorithm, we require data to train the algorithms. Okay, this is how the flow goes, and you might have make a lot of projects on that as well. Now talking about deep learning. In deep learning, we have neural networks. Some people have commented this as well. Neural network with couple of layers. Pooja has mentioned, and a type of artificial intelligence that teaches computer to learn. Massive computes learn how does human brain evolve. Yes. Okay. Somewhat it's correct. So in deep learning, we basically have neural networks. Now, what is neural network? That is a valid question. Now the thing is, whenever okay, how we learn as a human being, how do we learn? We learn from our experiences, right? But in a nutshell, if I'm talking very specific, we learn from our brain. Okay, because definitely it's observation, it's we are talking with people, we are watching videos, based on that we learn from experiences, we learn from people's experiences as well by learning. But basically, if I go in depth of deep learning, we try to mimic the way we learn. How we learn from our brain. Okay, now let's dig deeper into a brain. So if you know, in all of our brain, like all of guys have brain, means all of us human beings have brain. Some people might use it, some people might not use it, but that doesn't make any difference. We have brain. In our brain, we have neurons. The fundamental unit of that is neuron. In a neuron is basically a unit. For example, like this is how a neuron looks. Okay, it has axon, it has dendrite, it has nerve endings. So this is one fundamental unit of neuron. In our brain, we have billions of them. Okay, and they are interconnected to each other. Now, whenever I'm speaking, whenever I'm listening, whenever I'm singing, whenever I'm dancing, whenever I'm doing the hand movements, a certain set of neurons in my brain gets activated. Okay, gets activated, I mean to say data will flow through those neurons because we have billions of them directly, indirectly connected to each other. So in human brain, whenever the data flow through them, like a certain set of neurons will get activated when we are doing a specific task. In the exact same way, for example, if uh, you are talking to me about machine learning, okay, so in an area of your brain, uh, you already have the knowledge of machine learning, so those neurons will be activating. If you are you are learning a new concept of machine learning, some new connections are being made that's not already there in your brain, but means the connections are not there, neurons are there, so new connection will be made. And in deep learning and in human brain as well, we have a concept of neuroplasticity. Can anyone tell me what is neuroplasticity? No, definitely it's a topic of biology, but in neuroplasticity, it's a property of a human brain that the connections that we have in our brain can make and break. If you are learning about a specific topic more and more, the stronger the connection will become. And if you probably you might be reading a book probably an year ago and now you don't remember anything about it. But if you just see the summary of it, you might recall. Okay. So the stronger the connections are, the more you learn about it. But if you left something for some time, they start breaking up. Not exactly breaking up, the connection will start getting looser and looser. Okay. So this is neuroplasticity. The new connections can be made and connections can be broken. That's it about the biology. Now let's jump into neural networks. So in artificial neural networks, we try to mimic the same thing in computers. We'll have neurons, we'll connect some neurons, artificial neurons, they are mathematical functions basically. And inside those neurons, the data will flow. I'll make a neural network, artificial neural network, not biological neural network. From inside that neural network, I'll flow the data. When the data will flow through it, it will learn the patterns from it. And once it is learning the pattern, new connections are formed. Okay, some connection will become stronger, some connection will become weaker. And this is how a neural network and AI looks. You might have seen it somewhere as well. There are a lot of images already available. Today we'll decode this neural network as well. So this is how the neural network look. Okay, but they are mathematical function. Sorted. Now let's go ahead like to see what is there in one neuron. Once you have seen what is there in one neuron, you will understand the whole neural network architecture. Okay, and for that purpose, let me go to a website and here let me search perceptron. Okay, so this is the thing that I'm showing to you. This is one neuron. One neuron is called as perceptron. This is called as perceptron network, right, Anjali? This is correct. Okay, what is the difference between machine learning and deep learning? Both of them use data to train. But in deep learning, we have a specific kind of algorithm that's called as neural network. Okay, but in machine learning, we have a lot of different kind of algorithms. But deep learning is an algorithm that has the capability to revolutionize a lot of fields. So this is kind like one algorithm that will work on all the kind of texture, all the kind of tabular data. So that's why we have a new field, deep learning. Both of them works on data. Okay. Yes, perceptron is one unit. Perceptron is one neuron network. Okay. So now let's see how it will work. Imagine we have three inputs. In machine learning, you already have the knowledge what are new inputs, what are outputs, what is uh, like feature, what are labels. You already have that knowledge, right? It's ML subset of deep learning. Deep learning is a subset of machine learning. Okay. Now, if you look closely, these are the inputs of the network where three inputs will come. This is a neuron and this is the output. Okay. And here, if I go back, I can also increase and decrease the number of inputs. Think of it as I have four inputs coming in, and for four inputs, I want to have one output. Okay. This is the data that I want to get. This is just one sample. I have millions of such sample and I want to train a network. I'm going to train a perceptron based network where I have just one neuron. Okay. Now, if you look closely here, every input that is coming in is having a connection with the neuron. Okay. And these connections are called as weights. Every connection has its own weight. And this at the bottom, you can see this is nothing but bias. Okay. And if you know a little bit of linear regression that you have already discussed. So in linear regression, you know that we have weights and biases, right? What is the equation to find, what is the equation of a line? What is the equation of a line? So it's y is equals to mx plus c. Exactly. And if I want to draw the line in 3D, if I want to draw a line in 3D, what's the equation of the line then? So in 3D, it would be y m1 x1 m2 x2 plus c. So there will be two, uh, yes, there will be three independent variables, right? If you look closely here, here I have four inputs. So I will having four weights and one bias. Okay, that's the same thing. Perceptron, now this is basically the equation of linear regression. But now this weight has their, so this weight is random, this weight is random, this weight is random, this weight is random. So we'll do the same operation. W1 x1, W2 x2, W3 x3, W4 x4 plus this bias will give you the answer 7. Okay. Now here you can see step. What is this? This is an activation function. This activation function will decide if the neuron will fire or not, if neuron will send data to the next neuron or not. If so, what kind of data it will give. So here you can see we have sigmoid activation function, we have 10H activation function, we have ReLU, we have ReLU. So there are different kind of activation function. They will tell, they will basically decide, they are the deciding factor. What should the neuron fire? And this is the output. Okay. And if I go back a little bit, here you can see W1 X at W0 X0, W1 X1, W2 X2, W3 X3. Plus I have a bias. If I am calculating it, if I click on calculate, here you can see all the random weights with this one, which is 5, this one, and then if you go to 0.21 into 1, this one, this is another weight, this is another weight, this is another bias. So this is the output. Okay, so this is single neuron network. This is called as a perceptron. Imagine rather than having just one neuron, if I have multiple neurons, not one, not two, but hundreds of them, thousands of them. Okay, and here you can see every weight, you can see here we have 4 weights and 1 bias. So this model has 5 parameters. And this is also something that you might already know. Okay, how can we find the weights? To find the weights, we'll use an algorithm that's called as gradient descent. Okay, there are a lot of other algorithms as well that are in that particular direction, but basically we'll use the gradient descent for this particular use case. Okay, like OLS is there. In gradient descent as well, we have different types. Right now, we are going to use gradient descent. But this is just about how calculation is being done. This is not about how weights are found. This is about there are random weights in between in the beginning. And as we train the algorithm, the weights will get optimized. Every weight, you think of every weight as knobs. Okay. You might have used radio, right, in your homes. In radio, you have two knobs. First knob is of frequency. Second knob is of volume. So if you want to catch a frequency, you need to keep on tuning the frequency knob. And there will be a moment then you will say, okay, now the connection is being made. So you will take the setting then and there on. So rather than thinking of one knob, imagine if you have two knobs to check the frequency. Now you need to go for all the combination of both the knobs to see where exactly the frequency lies. Now this has 1, 2, 3, 4, 5 parameters. Think of it as 5 different knobs. You have 5 knobs that you need to tune to get perfect weights that will optimize this network. Okay. And this is a 5 weights, 5 parameter network. But you might have heard about some neural networks that has billions of parameters, that has billions of parameters. and literally trillions of parameters. And all these parameters are nothing but random numbers, but they are optimized. Okay, so parameter is nothing but numbers. So this is single perceptron. Now let's do one thing. Now let's go to a proper neural network. Okay, so here, if you look closely, this is a multi-layer network. We call this, we call it a neural network, a proper neural network. Okay, so here you can see we have one, two, three hidden layers, one input layer, and one output layer. Okay, this is a neural network, an actual neural network. Okay, in between we have hidden layers. At the first we have input layers. At the right we have output layer. Okay. Yes, it's a bit distracting, the chats. I'll take the chats at the end. That would be easier for me. Okay. So now if you look closely, we have four inputs this time. So this is basically a four feature, three label network, where we have four features, three labels. But in between, rather than having one neuron, so let me do one thing. Let me remove these layers so that it would be a bit easier for you. So earlier, if I am giving it, edit the number of neurons, and if it is a one neuron network, so here you can see it's just a perceptron. Okay, but now what I'm going to do, and here you can see there are four inputs coming in. These are the connections. So four weight, there will be one bias, and this is the output. But now what I'm going to do, I'm going to add couple of neurons in this layer. Let's go for 8 neurons. So now if you look closely, if I go to this, so you can see this neuron has their own weights, four weights, and one bias. And it also has their own activation function that will send the data to this neuron, this neuron, and this neuron. Same goes for here. Same goes for this. Same goes for this. So if I'm asking you, what are the total number of networks this neuron is having? What are the total number of parameters this network have? So if you look closely, you can also click here. So here you can see in first hidden layer to input layer, there are 32 weights, M into N connection, and 8 biases. So total 40 parameters are there. And in the first hidden layer to the output layer, there are 3 bias, 24 parameters, 27 parameters. So in total, this network has 67 parameters. It's pretty simple calculation, right? So 4 multiplied by 8, these are the number of connections here. 8 multiplied by 3, these are the number of connections here. And every neuron has their own bias as well. So we'll add that parameter. So eventually this network has 67 parameters. Okay. Now, what if I have more layers? What if I have one more layer? So now the number of parameters increases. And what if I will add couple of neurons into it? For example, if I'm writing 64 neurons, so here you can see the network. This network has 1163 parameters. Okay, but this is too much parameters. So let me reduce the number to 12 only. So this is the network. This is the neural network. So I have inputs, I have output, I have in between hidden layers. I can add as many hidden layers that I wanted, but after one time, after a threshold, the neural network will not learn. This is a traditional neural network. This is an artificial neural network that we talk about. Now, what I'm going to do, I'm going to discuss the problem statement, the project that we are going to make. Okay. Now, for 1 minute, I'll take the questions from you guys. If you guys have any question, do let me know. So use activation function and how to decide which activation we should use. We'll discuss it at the end. When to use ANN, CNN, and RNN. ANN is the neural network that you can see. CNN is a convolutional neural network. When we want to work on images, I'll use that. RNN is recurrent neural network, which I'll use if I have sequential data like text. What's the purpose of hidden layer? Hidden layer is just like, okay, treat it like a human brain. As a kid, as a child, the brain is not that developed, right? So it's not that big brain. The bigger the brain, the more neuron it has, the more patterns it can find, the better the model will become. Okay, so more the layers, the better the model. Okay, but in some cases, if your data is not that complex, or don't need to have that much complex model, Okay, is transformer also a neural network? Yes, it's also a neural network. It's also a neural network architecture. Okay, sorted. So now let's do one thing. Let's go to the problem statement of today's topic, and we are going to make a neural network for that. So now what I'm going to do, I'm going to take a data set, MNIST data set. So in MNIST data set, so this is a data set of handwritten digits. Okay, this has images from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So total 10 different classes that we have. And in the input, I'm going to give the image itself. So for every image, I have an output. I have 60,000 images in this in this data set. Okay, now tell me, this is which kind of problem is this? This is a classification based problem or regression based problem? This is a classification based problem where I have how many number of classes do I have? 9 or 10? I have 10 classes from 0 to 9. Total number of classes are 10, right? Okay, in this network, definitely the answer is 3. Now what I'm going to do, I'm going to train an algorithm on this, but not exactly this. There is a better version of this, which is called as FMNIST, which is for fashion MNIST. So this is kind of the same as MNIST, but rather than having digits, this has different kind of uh, fashion things. So we have pants, we have tops, we have t-shirts, we have shoes, sandals. So these are the different classes that I have. So now what I'm going to do, I'm going to take this particular data set, fashion MNIST data set, and I'm going to train the algorithm on that. Okay. So for that purpose, I'm using Google Colab. So let me create a new notebook for that. And at the end of the session, I'll also tell you about the assignment that you have to do. And on this data set, not one, but I'm going to train multiple neural networks. Okay. So first of all, as you, all of you guys are like familiar with Colab, right? Great. So now what I'm going to do at the side, I have a reference notebook as well. So I'm going to use the important codes, but like there will be a couple of codes that are needed. So for example, here are some important libraries I'm importing, NumPy, Pandas, TensorFlow. So I don't want to waste any time there. But here, if you talk about this, okay, so this is what we have. Okay, so here you can see I have imported Keras. Inside Keras, I have keras.dataset.fashionMNIST load data. So this one will help you load the data. You can also go for from keras dot datasets import fashionMNIST. You can also go with something like this. It will also do the same thing. From TensorFlow dot okay from TensorFlow dot keras dot dataset import fashionMNIST. Okay, so now if I'm executing this, so here you can see I have fashionMNIST here. So if I am executing fashionMNIST, so here you can see fashionMNIST dataset is here. If you want to know, okay, what are all the other dataset that TensorFlow provides? So the thing is pretty simple. Go here, go for datasets, and go for this. And here you will get a list of dataset you can directly import. Okay, you can write Cypher 100 dataset, you can write fashionMNIST dataset, you can write IMDb, you can import MNIST dataset directly. So we have the list of all the important dataset that's there. Now the thing is, let's go back here. Now inside this dataset, if you want to load the exact dataset, you need to use MNIST data dot load data. Okay, and this will return you 4 things as an output. Okay, now what are all these 4 things? So this will return you train images, train labels, test images, test labels. This is going to return you 4 things. And if you know the naming convention, you know what each of these variable is storing. Okay. So let's go for train images. Dot shape. I'm just printing the shape of it for now. So this has 60,000 is to 28 is to 28. Okay. So what about train labels? Dot shape, it has 60,000. Okay. So in test images dot shape, we have this, and test labels dot shape, we have this. So what do we have here? What are training images, training labels, test images, test labels? What are these values? What are these values? This is train and test data, right? So here you can see we have 60,000 images for training, 10,000 images for testing. Okay. And in train images variable, I have 60,000 images. Each image has the size 28 by 28. And in test images, we have 10,000 images with size 28 by 28. And in test label, I have the outputs, the labels of them. So let's do one thing. Let's print an index of it. So this is train image of index 0. And here you can see this is how the image looks. And you can easily recognize what this image is of. This image is of what? This image is of a shoe, right? Dark mode, I need to change the settings of it, but okay, hope it's better now. So train images, here you can see if this is how the image look. If I click on show data, this is how the data looks. If you look closely, we have these numbers. So you might get a bit confused, sir. How come this image is made up of numbers? How come an image made up of numbers? Any guesses? They are pixels. Exactly. All these things are pixels. And just if you want to know what are these pixels, I want to go for Tesla again. And here, let's go for. So if you look closely, I'm going to draw something. So here you can see black image, all the numbers are 0. If I'm going to draw 2 here you can see for this particular image, this is how computer treats this image. Here, every block you can see, this block is 1 pixel, this block is another pixel. So this block has the number 80. This block has the number 200. This block, this pixel has the number 255. So every pixel is a number, and that number ranges from 0 to 255. I'm talking about grayscale image by now. Okay. 0 means black pixel, pitch black. And on 255, we have pure white. And in between, we have shades of gray. And if I'm adding some blur effect into it, you can see this pixel is now like this pixel is 9, this pixel is 31. So this is how computer read images. Okay, so let's go back to the topic. So now you can see all these values are 0 because if you look closely on top, we have zeros written. Okay, so and if I want to show this image as Plotly, so I can also ask this Gemini to generate the image, plot this image with matplotlib. Okay, so this will generate the code to plot this image in through matplotlib. Okay, so that you can exactly see the image using matplotlib, and here comes the code, and here is the image. So I also need to add the color bar. Okay, use grayscale, use CMap as grayscale, because right now it's not showing it as a grayscale, it's showing it as a different color bar, but hopefully this is how the image looks. Okay, this is the same image as I have loaded, and this is an image of shoe. Okay, now this is the image now, and this is image number 0. From training images, I'm accessing first image. So if I go for training labels, look closely, okay? So if I'm taking training labels and going for the same index 0, so here you can see this is giving the output 9. Now what is 9? This is not 9 for sure, But basically, every output has a particular number given to it. This is just like indexing. So if it is shoe, I'll denote it by 9. Okay. So every shoe that you can see in the whole database, that will be denoted with 9. Okay. So now let's do one thing. Let's take some other image. Next index. So this seems like a t-shirt. So every t-shirt is denoted with 0 index. And let's take another image. So this is seems like a top, probably, I'm not sure. So this is index 0. So that means it's also a t-shirt. Okay. So let's go to index number 10312. This seems like a shirt. So this has index 4. So shirt has index 4. Now, what I'm going to do, now tell me what will happen if I'm going for 9999. Will it work? Will it work if I'm going for index 9999? How much indexes do we have in the data set? For that purpose, we need to go for dot shape. So you can see we have total 60,000 indexes. So maximum I can go is 59999. And this is a sandal. But if I'm going one after this, I'll get an error because I just have images till 5999. Okay, so these are the images and not just the images, these are pixel values. Okay, so this is the image, and because so this whole thing is going to be the input, and because this is an image of what? This is an image of, if I am executing it, of 9th index. Now, my AI is not going to understand this is a sandal. For AI, this image represent number 9. That's it. Because eventually I'm going to perform arithmetic operation. Arithmetic operation I cannot perform on text directly, right? So what I'm going to do, I'm going to take this image as an input, not just one image, but all the images as an input, and the output is going to be training labels. And they are to train the algorithm. And I also have another set of 10,000 images on which I'm going to test my algorithm if my model is working good or not. Okay, so this is the image that I have. Now, eventually, if once my data is loaded, as it is loaded as well, what should be the next step? I'm going to take the training images. I have loaded them. Now, for test labels, now let's see how the neural network will look. Okay, how my neural network will look. Now, it is going to be a classification based problem. And what is input size? Okay, now I'm going to do something that I think I should not do, but let's give it a try. Let's remove this layer. Now, how many input neurons I need to have this in this network? How many input neurons I need to have in this index? 10? I'm talking about input neurons. 6,000 inputs? No. 6,000 images are there, but every image is of 28 by 28 pixels. So I'm going to give one image as an input and the output is one of the 10 outputs. So the input of the network is one image, and one image is represented by how many numbers? It is represented by 784 numbers. And because this is represented by 784 numbers, and that's correct. So you can either say 28 by 28 or 784. So the number of neurons in the input layer is 784. Okay, I'm going to make it messy, but let's give it a try if it will not hang. So these are the number of input neurons I have in the input layer. And you can see it already has 6,000 parameters. Okay, and eventually, how many neurons I need to have in output layer? In the hidden layer, I'll change the things. How many neurons I need to have in the output layer? 10. Why 10? Because this is again a classification based problem where the output would be one of the 10 classes. So in the output layer, I need to edit the labels and it has to be 10. So this is how my neural network is looking right now. This is the input layer. This is the output layer. In between, I have two layers with 8 neurons each. Now, eventually, if you look closely, in the beginning, what I have? In the beginning, I have a very giant array of 784 numbers, right? I will, uh, I need to shrink all these 784 numbers into just 10 numbers. 784 to 10. So I need to keep on shrinking those neurons. So in the beginning, I have 784 neurons. So in the first hidden layer, I'll try to reduce the number, probably 256. And then in the next layer, I'll reduce it further to 128 or 64. And finally, I will have in the output layer already neurons, which is 10. So now I will reduce it down. I'll shrink it down. Okay. Why 10? Because I have 10 possible outputs. In MNIST dataset, fashion MNIST dataset, I have 10 possible outputs. It can be sandal or t-shirt or shirt or whatever glasses. Now, bear with me. If I click on this, here you can see these are all the networks, all the weights that this neuron has. So this has like how many weights this neuron has. Can you make an estimation? Just this neurons, how much weight this neuron will have? This neuron will have 784 weights. One bias, so total parameters would be 785, but 784 weights. Okay. And this neuron will also have the same number. Now what I'll do, I'll edit the number of neurons. And I can make it a mess. I need to turn this off as well, but let's give it a try. I want to go for 64. So here you can see this is how the network looks. So for this neuron, okay. So you can see these are the networks. Okay. So here you can see this has 50,000 parameters. And I was planning to make it 128, but it's fine because otherwise there will be too many neurons, and it cannot be shown. So now I'm getting back to the same thing because I don't want to mess it up. Otherwise, it would be difficult if the system get crashed or the browser crashed. So now what I'm going to do, I am going to take all these 784 pixels and give it to the network. But right now I have 28 by 28 size image. So I will reshape it to 784 one side array. So this is a two-dimensional image. I'll reshape it to one-dimensional. Okay, this is what I'm going to do. And eventually I'm going to train a network on this. But the thing is, how many neurons I need to have in the output layer? In the output layer, I need to have 10 neurons. Because I need to have 10 neurons, so, and in my current output, if I go for training labels, what is the shape? The shape is just 60,001 value, right? So now what I need to do, I need to take everything, for example, the 0, and convert it into one hot encoding. Now, what is one hot encoding? This is how it looks basically. So right now what we have, let's suppose the label is 3. Rather than representing it as 3, what I'm going to do, I'm going to represent it in one hot encoded format. Okay, so the output would be this list. This first 0 will represent the first neuron will not activate. The second 0 will represent the second neuron will not get activate. The third neuron will not activate. The fourth one will. Okay, so representing 3 will become this. So this is index 0, index 1, index 2, index 3. So at index 3, this label is activated. So this is how the output looks. Okay, so this is called as one hot encoded format. Okay, and to do that, this is the code which will help you, which will help me encode the text as well. But this is the sample images that I have. Now, once I have the data, I'm going to use the same from, and I can also go ahead with this. Like rather than importing it in this manner, I can write from tensorflow.keras.user from utils import to categorical, and I can pass this to categorical here. And because I want to perform it only on labels, so what I'll take my training labels and test labels because images will be as it is. While making the neural network, I'll flatten them into one dimension. So in training labels and test labels, I'm creating 10 such classes. Okay. And eventually if I'm executing it and printing now train labels.shape, earlier it was 60,000 is to nothing. But now train labels one hot encoded format dot shape is 60,000 is to 10. Now you might be thinking why 10? Because if we go back to zeroth index and go for zeroth index, this 9 is represented with this list. So that rather than passing it as one value, because at the output layer we have 10 neurons. So I need to have 10 values as an output. So that's why this neuron will activate, rest of the neurons will not for 9. And eventually for the next image of zeroth class, this neuron will activate, no any other neurons. This is how the loss is also calculated for the neural network. Okay, so now this is what we have. So eventually my data is transformed, my labels are transformed. And once my labels are transformed, in between, I also have some step that I'm skipping for now, but eventually we will reach there as well. So now I have 60,000 images for training and 60,000 their labels, 10,000 images for testing, 10,000 their labels as well. And now what I'm going to do, I'm going to build a simple neural network. This is a simple neural network. Okay, I'll explain you how this neural network works, but right now just make this neural network. Okay, so from Keras, so let's import Keras directly so that all the different kind of layers I'll import from here. Okay, so first thing you can see inside Keras, I have written keras.sequential. Now, what is this sequential? The sequential means basically that I'm initializing a neural network. It's just like initializing a stack, which is empty for now. So in sequential, I'm initializing a neural network where I will add layers. Right now, I have not added it, but I will add layers. Okay. So keras.sequential will initialize an empty neural network. Inside that, I will add different kind of layers. First layer is flatten layer. It will take the input image. Why I've added one extra dimension? Because eventually this whole thing is going to be a matrix multiplication. Okay, so I need to treat it as a tensor. That's why I need to add one extra dimension. And to add this extra dimension, I also need to write the code here, like the way we have transformed the labels. I also need to transform the features so that every image of 28 by 28 size will have 28 by 28 by 1. So this is nothing but adding an extra dimension. That's it. The data will remain the same. So here I'm adding a flatten layer. So flatten layer will take a 28 by 28 size image, convert it into one dimension. That is it. It will not do any fancy operation, just converting a two-dimensional list, two-dimensional array into one dimension. That is it. So that the neural network will have 784 neurons in the input layer. That's it. And once the first layer has 784 neurons, then I have initialized the next layer, which is the first hidden layer, has 128 neurons. Then 64 neurons, next one, then 10 neurons. Then you might be thinking why I'm shrinking it down, because in the beginning I have 784 values. I need to keep on shrinking it down till 10 numbers. That's what I need to do. 784 numbers, shrink it down to 10 possible outputs. That's why I'm reducing the numbers. Now let's see about this activation function. As I've told you, every layer, every neuron will have an activation function. So here as well, if I talk about this particular layer, all the neurons in this layer have a common activation function. Same goes for this one. The whole layer has a common activation function. This layer has a common activation function. So does output layer. Okay. Now you might be thinking, sir, I understand. Okay, this is an activation function, but why do we have different activation functions? Okay. And for that purpose as well, I might have something. It's called as activation functions. So if I go to sigmoid, so this is how sigmoid activation function works. So if here you can see, let's go for an auto run. So if the value is very negative, So you can see if the value is 5, the value's output is very close to 1. Okay, as you can see here. If the value is very negative, if the value is, for example, -5, it is close to 0. But when the input is 0, the output would be very close to 0.5. So if I want the data, my output to be in the range from 0 to 1, then I will use sigmoid activation function. Okay, if my output should be ranging from 0 to 1, I will be using sigmoid activation function. In the exact same way, I have 10H activation function where the value lies between -1 to 1. So if you want this kind of output, go for 10H. In ReLU activation function, here you can see if the input is negative, it will take 0. But if the input is positive, it will take the same value. So ReLU activation function will neglect all the negative outputs. It will only pass on the positive values, right? And in leaky ReLU, it's kind of the same, but here you can see rather than having 0, it's slight negative. If we have a negative value, I'll make it very small negative value. And if it is a positive value, I'll take it as it is. We also have step function, which will take 0 or 1 in between. It will not take anything. Now tell me, in this architecture that I have defined, why am I using ReLU activation function? ReLU activation function, if you look closely, eventually it will not take any negative value. If the value is positive, it will take the value as it is. Why I need to use ReLU activation function in this? Why are we using flatten first? Because I'm using a very basic neural network of only the neurons, dense layer neural network, ANN. I'm not using a CNN based network. I am going to use CNN based network as well. In that case, I'll not flatten the layers. Back propagation, pixels can't be negative. Okay. So pixels are the input. Eventually, the calculation I'm performing, that can be negative. Why I'm using ReLU activation function? Because tell me what should be the possible output? What should be the possible output? The possible output should be a list. And in the list, all the values should be closer to 0. And the value of that particular index, that image should be closer to 1. Because the output looks like this, I want the output to look like this. I don't want any negative value. Okay. And in between as well, I'm passing the data in the exact same format. That's why I'm using ReLU activation function. Okay. And here you can see if you click on compare all, this is step-by-step comparison of all the activation function. They are not all the activation functions. Now I'll jump to the last activation function, softmax. Now what is softmax activation function? Well, that's something I'm skipping for now. When I will train the model, and once my model is trained, then I'll discuss about this. And then you can understand in a better manner as well. And here, once my network is defined, so here you can see I've defined my network. It has two hidden layers, one output layer and one input layer. Here you can see once my network is defined, I will compile the model. It's a same like I've defined the model. How will the model will learn? How will the model learn? What will the model give as an accuracy? So it is going to print accuracy. It is going to find the loss, which is categorical cross entropy. I'll discuss about that. And here is the optimizer that will basically decide based on which kind of optimization you want to update the weights of the model. Okay. We have different kind of optimizers. Adam is the optimizer that will work great in almost all the cases. You can also use SGD, stochastic gradient descent, which is very slow to work with. And what is this categorical cross entropy? Imagine if I have just two classes. Okay. So in that particular case, the answer can be either 0 or 1. If the answer can be 0 or 1, which activation should I use? I can use sigmoid activation function, right? So in that particular case, I can use here sigmoid activation function. But now I have 10 separate classes. So I want the probability distribution, like what is the probability of this image to be class 0, this image to be class 1, class 2, class 3, class 4. So the softmax will give you probability distribution. And whenever you have multi-classes, more than two, the law should be categorical cross entropy. If it's a classification based problem. If it is two classes, you can use binary cross entropy. And you can also use mean squared error loss if it is a regression based problem. Right now it is not. So this will compile the model. And eventually if I click on model.summary, this is how the model looks. And if you look closely in the input, I have 784 neurons. And in the first layer, how many neurons do I have? 128 neurons. So what are the total number of weights I'll have? 784 multiplied by 128, which eventually is 100352. But they are just weights. I also have biases. How many biases do I have? 128, which will eventually give you 100480. This. So between the input layer and the first hidden layer, we have 100,480 parameters. And what about the next layer, where I have 128 neurons to 64 neurons. So these are the total number of weights plus 64 bias, 8256. These are the total number of parameters here. And in the output layer, we have 64 neurons input. And in the output layer, we have 10 neurons, 640 plus 10 biases, 650. Add all of them, we have 100,000 parameters. Very simple calculation. Very simple calculation. What is the end goal of this model? To make a model that can recognize out of one, like if the given image is of a t-shirt or a sandal or what. Okay. So this is the model summary. Now what I'm going to do, I'm going to train my model. And to train the model, I will just use a simple one line of code to train the model, which is model.fit. And here, this is the one. Now, I will use model.fit, and inside that I'll pass what are the images. Images are training images. Output is one hot encoded. I want to train it for 30 epochs. Now, what is an epoch? What is an epoch? An epoch means how many times you want to go through the whole data set once. It seems like if I'm giving you a set of 10 questions and I want you to solve them, if you have solved them once, you can say I've learned it, but that's not enough. If you solve them twice or three times or four times, you can learn in a better manner. So in the exact same way, going through the whole data set once is not enough. So the best thing you can do is go for multiple epochs. So right now I want to go for 30 epochs. Then we have batch size. Right now, let's go for one batch size and then we'll see what exactly we need to do. If I'm executing it, I'll get an error. Okay, I've not got an error. That's great. Okay, so basically what's happening now? I've loaded the images. I've transformed the labels. I've defined my first network, which has 100,000 parameters. And now I'm training the model. And here you can see, so far it is training the first epoch. We have a total of 30 epochs. One epoch will take 2.5 minutes to train. And here you can see right now the accuracy is 0.46. 0.46 means 46%. 46% is a decent accuracy because even if I'm guessing at out random, we have total 10 classes, right? Even if I'm guessing out random, one of the 10 times, one out of 10 times I'll be right. So the baseline accuracy is 10%. If I'm getting anything more than that, that means my model is learning. And right now the accuracy is 40% and the model is learning. And if you look closely, it is taking one image at a time, pass it to the neural network, predict the labels. Okay, as per current model. But eventually the issue is whenever you are training a model, in the beginning, the output will not be correct. So it need to back propagate, update the weights, and then calculate the error. Okay, then you need to go for the another image, calculate the if the model is predicting correct output or not, and then back propagate and update the weight accordingly. So it's same like take an image, get the current output based on current weight that are random. That will not be correct for sure. Like 1 out of 10 time it will be correct, but most of the time it will not be correct. So what it will do, will take the current output, expected output, will find the difference. That is your error. Error for one image. The same error we will calculate for all the 60,000 images. And that average error is called as your loss. And this loss you can see is 4.1. I need to minimize this loss. Lesser the loss, the better my model is. Okay. And right now you can see I'm going through all the images once, and I am, how many times I'm updating the weight? I'm updating the weight 60,000 times for one epoch. So that means 60,000 times for one epoch. For 30 epochs, my model will update the weight 18 lakh times. 18 lakh times is a lot. Okay. So eventually, a sweet spot is go for 10,000 or 20,000 time weight update. That's the best you can do. Okay. And here you can see once the first epoch is done, it will take the test data and try how well your model is performing on unseen data. The same thing you have done on the earlier machine learning models as well. Okay, so now it is training it on test data, and here you can see on test data, the model accuracy is 15%, but training accuracy is 34%. Now it will start the training for second epoch. Okay, so now what I'll do, I'll stop the training here. And what I'll do, rather than going for updating the weight after every epoch, I'll get a batch of 64 images, or let's take 60 images. So now I'll take what I'll do, I'll take a batch of 60 images, calculate the error, and then update the weight. After a batch of 60 images, I'll update the weight. How many images I have in total? 60,000 images. And one batch is of 60 images. So how many batches I will have? If one batch has one batch has 60 images, total I have 60,000 images. So one batch will have 1,000 images. So this is called as batch training. And now you can see earlier, and here you can see there is a drastic difference. Earlier to train one epoch, I need 2.5 minutes. Now to train an epoch, I just need 5 seconds because less calculations are happening. I'm updating the weight less frequently, 60 times less frequently. Earlier, I was taking one image, updating the weight. Now I'm taking 60 images and then updating the weight. So weight update is 60 times less, right? So this is a huge difference. So eventually, if I want to train this model, and here you can see the accuracy. Earlier, if I'm okay, imagine in that scenario, I was training the model for 2.5 minutes, still the accuracy is 30%. Now I'm training the model for less than a minute now, but still the accuracy is around 65%. And on test data as well, I'm getting 65% accuracy. So if your data set size is huge, play with batches, play with batch size, and accordingly the model will train. And here you can see I'm updating 1000 of it. So 1000 means 1000 batch. One batch will take 4 milliseconds to calculate. And if I go to runtime, change the runtime. Right now I'm using CPU. If I click on T4 GPU, the training time will reduce further. Okay, so using a GPU is needed in these kind of scenarios. Okay, let's go back to the same thing. So now I have trained my model, and my model right now is at 73% accuracy. Okay, so let's do one thing. My model has started the accuracy from 40%. and training accuracy 22%, testing accuracy 44%. Now my model is at 74%. Now tell me, if I stop the execution of the model and I want to train it for 10 epochs. Right now, when I have initialized the model, all the weights are initialized at random. But now I have trained this model for a couple of epochs. Okay. And I've stopped the execution in between. So the weights are updated, right? Weights are updated to maximize the accuracy. Now tell me, if I'm executing this again for 10 epochs, the accuracy will start from 22% or it will start from 74%. The model will start from, accuracy will start from what? It will start from the totally random weights, or it will start from the weights that are already trained. So most of the people are correct. If I'm executing it again, the accuracy will start from means more than 75% because the model already has the knowledge. The weights are already updated. Okay, but again, if I'm stopping the execution, go back, initialize the model again. Now this model has all the random weights. All the train weights are gone. Now if I'm training this model for 5 epochs, the accuracy will start from scratch. Okay, though you can see the accuracy, why the accuracy is starting from 50%, but again, the weights are randomly initialized. If it is starting from the very beginning, it should start from like 82%. But now the model accuracy is starting from very random. And again, if I'm copying this, pasting it here and executing it again, here you can see the accuracy is not starting from 70%. It's starting from where we left. Okay, so you can retrain the same model for multiple epochs as well. So now after this iteration, I cannot say the model is trained for just 5 epochs. Right now, the model is trained for 10 epochs. Okay, and you can change the step further. If I want to go for example, 128 batch size, train it. And eventually, if I'm initializing the weights out of random, so that would be better. So here you can see this is what I have. So the model took just 2 seconds to train, and here you can see the accuracy in just first epoch. The accuracy is 88%. So here can you see, just by changing the batch size, earlier it took me 20 like 2.5 minutes to get the accuracy 30%. 2.5 minutes. Same network. But now, just because I've changed the batch size, within just 10 seconds, 15 seconds, I've got a model with 90% accuracy. That's great, right? And it's just about changing the batch size. Okay, lesser the base size, more the weights will train. Okay, so here you can see this is a very basic model that I have trained, and this is giving decent accuracy. Now, what I'm going to do, the issue with this model is right now what I'm doing. Exactly what I'm doing, I'm showing you that. So right now, what's happening? I have 3 layers, but imagine I can have multiple layers as well. In the output layer, I have one out of 10 outputs. And if I'm drawing 2 and click recognize, every pixel will be converted into 1 dimension, and the data will flow through the neurons. And eventually in the output layer, it will be decided that which neuron should be activated. This is the network that we have made. What is the biggest issue with this kind of network? Any guesses? This Rahul got the point. The point is, why don't we use convolutional layers? Convolutional layer is the answer. But the issue with this is, I'm taking this image, converting into 1 dimension. If I'm converting an image into 1 dimension, all the features of this image is gone, right? The major features of the images can be seen easily if it is in 2D. Imagine if I'm changing this image, converting it to one dimension giant array. What can you see? You cannot see anything, right? So that's the major issue with ANNs. ANNs cannot work great on images. So what to do? We need to use a network that is called as CNN. Okay, the way we have added dense layers, we can add convolutional layers. Now, what is there in convolutional layers? Let's see. So imagine if I'm drawing the same image of 2, I will generate different versions of the same image. Okay, and then reduce the size it to 1/2 and increase the different versions. So here you can see, I will take 4 version of the same, 6 version of the same image. But after that, I will generate again double the size of like right now what I'm doing. Okay, let's recognize it, then you can understand in better manner. So here you can see, I'll generate different versions of the same image and then convert it into a dense 1D array and then passing it through. Okay, so the benefit of it is because I have different version of the same image, some neurons will activate for the upper curve probably, some of them will go for the lower curve, some of them will go for edges probably. So this is the kind of thing that CNN will help you because it will take the image as it is. Okay, and to give a visual representation, this is how CNN works. So if I'm drawing the image of 2, okay, so here you can see this is the original image. Now I'll generate 6 different versions of it through convolutional layer. And here you can see if I am going to this particular pixel. So this pixel is made up of, sorry. So if I'm going for this particular pixel, this pixel is made up of the input from these six pixels. Okay, so this, and in the exact same way, this is the output I'm getting from these 6 pixels. So basically, I'm doing image convolutional operation on this, through which I'm generating different features from this image. And then here you can see the image size is almost 1/2 because this operation is called as pooling, where I'll basically take the original image, reduce the size of it to 1/2, but pixel by pixel. Here you can see in this particular case, if I go to this pixel, so this pixel will take these 4 values, take their average values. So 4 values means 4 numbers, take the average value, give it here. In the exact same way, for this particular pixel, it will take these 4 values, take the average, add it together. Okay, so this is max pooling. Then we'll add convolutional and max pooling. And eventually, all these features you can see, these features will be converted into one dimension. Okay, and once they are converted into one dimension, after that, it is just a dense neural network. So at the bottom, you can see this is a convolutional layers with max pooling layer, so that I can take different feature of the same image, keep on shrinking the image down so that I can have more features of that, more filters of that, and eventually I'll have neural network, dense neural network. So what I'm doing here, rather than using a traditional neural network that I already have that is working as well, I will use the same network, but this time I will also add some convolutional layers in between. Okay. And for that purpose, I'm going back here. Okay. And usually what's happening here now, let me wrap this code for you, where everything is happening in the kind of the same manner. I'm loading this data, and here I have added the cannot connect due to limits. Okay, go ahead. Because I might have exhausted this week quota, this week free quota for this. But if I go here, what will happen? This is the basic neural network that I have trained. Now, here, if you look closely, I have made a neural network which has dense layers, which has flattened layer as well. But in the beginning, we have convolutional layer and max pooling layer. Again, one more convolutional, one more max pooling as mentioned here. So you can see this is convolutional layer. As you can see here, you can hide a couple of the layers as well to make the things easily visible. But if I show you, this is the layer that is just shown. This is first convolutional. This downsampling means pooling layer, max pooling layer. This is another convolutional layer, and this is another downsampling layer. Okay, so that I'll reduce the image size. So it's just like keep on reducing the image size and getting different variation of the same image. So that rather than having one big image, I have 100 different smaller images. Each image will have different features of it. So here you can see, right now you cannot see anything like these feature does not make any sense, but for computer they does. So now eventually this, first of all, we'll take these existing images. Okay, right now, okay, it's connecting. Why it's not connected? Okay, it's fine. I can directly copy paste this neural network as well, and I can make it work. So this is the traditional neural network that I've already trained. Now what I'm doing, I'm going to train one more network. And in this network here, you can see flatten layer and dense layer is something that you can easily understand. But inside this convolutional and max pooling layer and another convolutional and another max pooling, in these convolutional layers, there are 320 parameters of just the filters. In max pooling layer, we are taking 4 by 4 size grid, go up and take the average. So in that case, we don't need any parameters as such. So that's why we have 0 parameters. Here we have couple of parameters because we are converting everything into, we have some features here, and eventually these are the total number of parameters in this layer. Okay, this is the model summary, and eventually once we have the model summary, I can train that model as well. And to train this model is called as basic CNN model. So let's train this basic CNN model and see how the accuracy will differ. I'm using everything kind of the same way. And let's see if it's being trained. And here you can see everything is the same. Like here, I'm also training for 5 epochs. I'm using 128 bash size. Here it's also the same 128 bash size. Here it took 2 seconds to train. Here it will take around 30 seconds to train. Why? Why this is happening? Because of max pooling? Not just max pooling, because we are using, yes, simple answer is we are performing more operation. We are using more complex operation. We are using convolutional layers. Convolutional layer will take more time because it has a lot more operation to perform. Okay, so that's why it will take around 45 seconds to train. And eventually this model, if I'm training it for like 10 or 20 epochs, will give you better accuracy than a traditional ANN based model. Okay, and eventually if I am training it for these many models, what I can do, I can go back and train it for even deeper network, even deeper model, where I have more layers, more batch pooling. Like earlier, I was having two set of convolutional and max pooling. Now I have convolutional max pooling 3 times. So I have even deeper network. So I'll have more parameters and it will take even more time to train. So more complex model you will have, the more features it will find, but you don't need to have very complex model in some cases. If they are just, okay, now tell me one thing. I want to train two models. One is on MNIST dataset with these images, and another one is on Fashion MNIST dataset. What are the chances that if I'm using the same model, same ANN model, which dataset I can get better accuracy? On which dataset I can get better accuracy? Numbers, MNIST. Okay, all of you guys are saying MNIST. Why MNIST? Some of them are saying fashion MNIST as well. Why MNIST? Why on MNIST I will have better chances of getting the accuracy? Because less features? No. Because 10 labels? No. Both of them has 10 labels. MNIST seems easy. Exactly. MNIST don't have a lot of features, lot of complex features. Okay. As you can see, here we have very complex things as well. But if I'm talking about images of 0, 1, 2, 3, it seems simple. So even ANN based network with no convolutional layer can also converge, can also give you a very good accuracy. But if the data set is like Fashion MNIST, where the images are having a lot of features like this. So in these kind of cases, it's not like ANN will not work, but will not work as great as a CNN. Okay. And right now I'm using images size of 28 by 28 or 32 by 32. In actual, the images size can go to 720 by 720. So in that case, you can see 720 by 720, 518,000, 580,000 weights, inputs, neurons I need to have. If I'm using ANN, if I'm directly using ANN for a 720 by 720 size image, I have 518, 500,000 neurons in the first hidden layer. Then I cannot directly shrink it to 128. It should be 580,000. It can be probably like 10,000. Then it can be 2,000. It can be uh, probably 512 and 128 and eventually reach there. Okay. And because this is the whole flow, this is how the flow goes. So I cannot directly use ANN for large size images, very high density pixel images. Okay, so because of that only, I'm training a CNN based network, and here you can see it is giving 90% accuracy for 5 epochs. And what about this model? This model was giving me 89% accuracy for training. For validation, 86%. Here validation is 87%. And right now the model is just trained for 4 epochs. So the accuracy I'm getting here after 3 epochs is same as accuracy I was getting there after 5 epochs. Okay, it seems simple, right? Here you can see I'm training a CNN with a very basic network, and here you can see this is how the model is giving you the accuracy. This seems fine, right? We can add more number of layers, we can train it for more epochs, and we'll get a better accuracy. Now the thing is, how can I get output from this model? This is my main agenda now. Now my model is trained. I can train, once my model is trained, I can save this model as well. For example, I can take this basic underscore CNN model and I can write the model save, the save weights, and after using the save weights, I can save this model as well. And eventually, once the model is saved, I can anyhow use it. I can use it whenever I want. I can even do this thing that I have done it as well. If I go to GitHub, I'll share you the links. I've trained my best model that has gained the accuracy of 92, 93, 94%. And I've already made it. I'll give it to you. You can also load these models using Keras functions. So in Keras, there is a function called as load model, load underscore model. So from that function, you can load any model and you can use it anyhow. Now, what I'm going to do, I'm going to write the code so that you can take any image and give it to the model and see if the model is giving you the output or not. So what I'll do, I'll take one of the model. For example, I take basic underscore CNN model. And if I execute it, this is the model that I have, dot predict. And in the prediction, what is this model going to take as an input? This model is going to take as an input an image of 28 by 28 size, right? And because the image size is 28 by 28, so the easiest thing I can do right now is take one of the image from the training images. So I'll take training images, take first image, the image size is 28 by 28. So if I'm giving directly to this model will give you accuracy. That input shape is 28, but the model is expecting 28 by 28 by 1. I need to add one more dimension to it, right? So what I can do, So I can take this and I can write np dot expand dims function, and x is equals to 1 probably, and it will expand the dimension to it if I'm writing the shape of it with the correct spelling of shape. So, okay, it should be 0 at 0th index. Yes. So now this is something I'll give to the model. So I'll take the image, I'll expand one dimension to it, and I'll give the model. And this is what I'm getting as an output. Now, can you please tell me what this output is? And kind of the same thing I'll also get. This is basic CNN model. I can also use basic CNN model. Okay, the model name might be, okay, basic CNN model, and the model name is ANN model. Okay. So I have also taken the ANN model. This is also giving you this particular thing as an output. What is this list of numbers? They are weights? No, they are not weights. At the end, I'll summarize the convolution. I'll summarize at the end the theoretical part of it. Don't worry. Okay. This is probability. Exactly. You remember when I was uh, training the model, the outputs I have encoded into this format. So for every input, the output would be a list of numbers, right? So this is what the model will give you as an output. And this is the exact same thing. These models are also given you as an output. This is a list of 10 numbers. Okay. And if the output is this, what does that mean? That means the image is of the label number 9, right? And so if I am going here in this particular case, if you look closely, they are exponential numbers. So 1.46 is to 10 to the power minus 12. 10 to the power minus 12 means a very small number. Okay. Minus 13, very small number. Very small number means 0 and 12 zeros. Means after decimal 12 zeros and then 8. Very small number, very small number, very small number, very small number. And this is 9 into 10 to the power minus 1. So here the answer is 0.999, which is equivalent to 1, right? So that means this image is of label 9. This image is of label 9, right? And that's great. That's exactly what I wanted. So what I can do, I can take this array and can I do like a for loop for it? I also want to know, okay, this is an array, this is index 0. Okay, so I can go for loop, right? For I in this, print I. So this will print all the values one by one. And this is the label, and I can also use enumerate. If you don't know what enumeration is, enumerate will basically not only give you the output, but also give you the index that we want in this particular case. So I want the I and sorry. So first is index and second is the label for the output. So if I want to print the input at the output, so you can see for index 0, this is the output, index 1, this is the probability. Now, if you look closely about all these numbers in this format are given because of an activation function that's called as softmax. So now to summarize, softmax function will give you what? A probability distribution. That, for example, for this particular image, the output is 9. And my model is very confident. 0.999. My model is very confident that this is an image of this. And the exact same way, I can also use the same code to get the prediction out of the ANN model. And here you can see my ANN model is also giving you the same output, but here for this model, the chances are this model is not that confident. Okay, CNN is very confident. This model is not that much confident. Okay, so it's totally up to you which one would you like to take. Okay, that's why I was saying CNN works better, a lot better on images than ANN. On some very basic images where the image size is 28 by 28, 32 by 32, or 128 by 128, 64 by 60, 64 by 62, 64, it can work. Okay, but if the image size is not that high, then it will not work. Okay, so now this is my basic CNN model. Clear? Now the next thing is this will give you the probability distribution. If you want exactly which index the output lies, you can also use like there is a function np dot arg max, I think, if I'm not wrong. So I can use this output that I'm getting from the model, giving it back to the arg max function, and it will give you the exact output at which particular index you are getting the maximum value. So rather than printing the whole map and all the different things that I'm doing, directly go for argmax function. It will do the rest of the things for you. Okay. And if I look closely, which image I have taken train images of 0th index. This was the image of a shoe. And if I want to take the label of it, what is the label? I have already discussed about this as well. This image, what is the label of this image? The label of this image, in actual, the label of this image is also 9 because shoes are represented with the 9. That's something we have discussed as well. Like if I want to exactly check the label of it, so you can go for training images, training labels, and inside the training labels of 0th image is of 9. And that's what my model has also predicted. So that means my model has learned it. My model is working. In the exact same way, I can also go for some other image. Let's go for another index. So this image is of 8 as per the model, means 8th index value. So let's go for the exact same image. This is a purse. And let's see what is the exact output. It's same. It is the same. Okay. Now, this is what I have. Now, what I'm going to do, I'm going to download an image from the internet. And once I have downloaded that image, I'll give it to this model and check if my model is predicting it correctly or not. And for that purpose, let's take a shoe. That would be the best thing I can do, I think, for now. So let's go to internet. Let's like shoe image. So I've got a shoe. Let's take this image. And here, it would be better if I can get a square image, but because my model will not take any image as such, it should be a square image. So let's take uh, which image should I take? Let's take this image. Let's open this image in new tab. Okay, that's not square as well. Let's do one thing. Let's take a screenshot of it. It would be easier. So I've taken a screenshot of this image. This is the image that I want to take. Okay, I've taken a screenshot of it. I want to upload now. My model is here. So I need to upload the image here as well. So let's upload the image. Go to desktop. This is the image that I have taken. So let's upload it. So here you can see it is uploading this image. I can also write Python script that can download the image directly from the internet, but let's rename the file. This is image dot. Okay, this is the image and this is the PNG file. This is the image that I have. Image.png. Now I need to write the code to load this image. Okay, so now I'm asking Gemini to write the code for you, like code of Python to load an image. Okay, and I can also mention use OpenCV, use Pillow, use any library of your choice. I can be specific as well. And here you can see it is using OpenCV. Here I need to give the image path. Just copy the path, give the path here, and execute it, and if I check the image dot shape, so this image is of 684 by 896 by 3 size. Okay, and I want to predict what this image is of, and I like go to plot this the image. Sorry, I shouldn't have done it, but okay. So this is we go to plot the image, and now I'm again going for load the image. So this will plot the image using plt.imshow. So hopefully this will plot the existing image as well. Okay, okay, it's not doing in that way, but now if I'm going for this image specifically, let's leave it here because my image is loaded. I don't want to go there. Stop the execution. Why it's taking so much time? It will restart the kernel. Okay. I think I need to do this. I don't want to, but I have to. Okay, let's go ahead. So now let's summarize whatever we have done so far. So I'm loading the data set, training an ANN based model. I'm importing Keras. So the Keras is imported. And this time I'm not training a CNN network. I'm just training an ANN network now, right now because I don't want to uh, spend a lot of time there. So here you can see this the model. The model will be trained in just first couple of epochs. And in this model will not work because this model is not loaded. But I'm using this basic ANN prediction. And if this is working, that means the model is giving you the output. And then eventually you can use argmax for the basic ANN model. And now I'll write the code to load an image. Load the image in Python. So I'll use copy path. Here is the path that I'll give of the image, and the image will be loaded. And this time it's using MPIMG. That's totally fine. I'm pretty fine with it as far as the image is loaded. So this image is loaded now. Okay. So here comes the image, and if I'm printing the image dot shape, so this is of this specific size. Now, can I pass this image directly to my network? No, right? Because my model is designed to take an image that is 28 by 28 size. So I need to resize it to 28 by 28, right? So now I'll ask ChatGPT to generate a code to resize image to 28 by 28. Okay, okay. So to write the code to resize this image to 28 by 28. Okay, if we can use cv2 function, yes, it's doing the same thing. So it's importing cv2. So I can also use this. Like this is the existing image that I have. So I'm importing cv2. I'm loading this image. And here you can see I'm printing image.shape. This is going to be okay. Thank God it's not gone yet. And this is resized image.shape. If I'm executing it, here you can see earlier the image is of 128 by 128, like 6054. Now it has 28 by 28, and this is having 4 channels. I need to convert it into RGB as well, into grayscale as well, right? Because the image is not grayscale yet. Convert this image into grayscale. Okay, so in CV2, I have CV2.CVT color function that will help you convert the color. CVT color function that is being updated. and eventually I'll take the resized image. I'll take this resized image and I'll take the grayscale image. And if I show the grayscale image dot shape, this image will have 28 by 28, exactly the image that I can give it to my network. Now what I can do, I can also copy this, okay, plot image in every step as well. Okay, so now hopefully it will write the code that will plot this image in every step, because eventually what I want to see the image in every step as well, how the image looks. Okay, and here it has done something. Let's run it. This is the original image. This is the resize 28 by 28. And this is how the image looks after converting into a grayscale format, but this is not the grayscale that I was expecting. Okay, so I hope you got the point, right? So here comes the 28 by 28 size image. Now what I can do, I can give this 28 by 28 size image to my network. So right now I have built the basic NN model. I have not trained another model. Basic NN model is already trained. It's trained, right? Yes, basic NN model is trained. Internet connection unstable. Basic NN is not defined. Can this, how come this possible? Okay. Uh, basic CNN model. Okay, have I trained basic CNN model or basic ENN model? Okay, this model is trained. Okay, let's train it again. Basic. Obviously, I was calling her by wrong names. How come this model be existing out of nowhere? So this ANN dot model, I can pass dot predict what this grayscale image. And you might already know this will give you the same error as earlier. That image is of 28 by 28, expecting 28 by 28 by 1. So I also need to expand a dimension, and I can use the exact same code of np dot expand dimensions of this with x is 0. So np dot expand dimension of this image with comma x is equals to 0. And now my model is predicting something. And my model has predicted a very vague range. Okay. And at the meantime, let's do one thing. Let me train the CNN based model as well, so that I can also make a side by side comparison of which model is working better. Obviously, it's going to be CNN. But here you can see my model is predicting this. This like 10, think of it as like 10% chances of being this class, 6% this class, 12% this class, 12% this class, 8% this class. Means my model is not confident. Though my model is predicting it, but my model is not confident about anything. Okay. So even if I am passing it inside np.argmax, it will give you one single output. But my model is not confident that this image is of a shoe or a sandal or what. Now let's do the same thing with CNN base network that we have trained. So this is a basic CNN model. It's being trained for the second epoch. I need to wait for 2-3 minutes to make it work. But eventually, once it's gone, you can use that model as well. Basic CNN model. So if I'm executing this one, so this one, I'm not saying this one will be great, but this one might not be this pathetic, right? This model is not at all that great because, as I've told you, ANN are not great for images. CNN are great for images. So your task is to build at CNN. Okay. So eventually, meanwhile, while the model is being trained, let me summarize everything that we have done so far. Okay, so first of all, we started with a neural network. What is a neural network? A neural network is all about uh, we have brain as a human being. All of us have brain, and this brain has neurons, and this is the reason why we learn. We have the concept of neuroplasticity through which the neurons can make and break connection based on the things that we are doing. If we are learning about a specific thing very passionately, so stronger the connection will become and weaker the connection will become if I let that topic for a couple of weeks or months. So this is neuroplasticity. The same kind of approach we'll try to apply on computers using artificial neurons, which we call it as a perceptron. Then we have seen a perceptron. In the perceptron, it's just like a linear regression kind of a thing where I have multiple weights and biases. I've shown you a perceptron as well. And then we have seen how weights are decided and bias is decided. What are parameters of a model? We have not discussed how these weights are calculated because that's a very lengthy process. That's how gradient descent works. Uh, but I'll share with you a notebook where it's mentioned how gradient descent can be performed uh, from scratch. The algorithm from scratch. I'll share you that resources as well. Okay. And once we have done that, we jumped on neural network, proper neural network where I don't have just one perceptron, I have multiple neurons. And along with that, we have seen how we can have not only multiple neurons in one hidden layer, how we can have multiple neurons in multiple hidden layers. Okay, that's also something we have discussed. Then we jump on how CNN is different. CNN is not converting an image into one dimensional. It will take, first of all, do the feature extraction part. This convolutional and max pooling layer, they are doing the feature extraction part. They'll take the image, generate different version of the same image, extract different features from it. And once it has extracted enough features, then we are converting into one dimension. And then the rest of the network will be a dense neural network, an artificial neural network. This is how the whole process will go. This is how the flow will go. Okay. And eventually, what we have done, we have trained both the networks. For the same use case, I've trained a ANN. For the same use case, I've trained an CNN as well. Okay. And once I've trained both the ANNs and CNN, then we have done a comparison. Okay. And here, this is the basic CNN model. I'm not saying the output should be great, like great, but output should be decent. Okay. And now plot this image. Model is being trained right now. Yes, model is still just 4 epochs. It's not until 5th epoch. So I need to wait for it again. And here you can see this the gray image that it's gonna plot. That's totally fine. I want to string shift it at the bottom. So once my model is trained, I'll do it. Okay. Now let me take you to this notebook. Okay. This is a perfect notebook which has everything. Starting from the basics, we have data being loaded, we have features converted to labels. There's also a process called as data normalization where the image pixel are ranging from 0 to 255, right? If I want to normalize all the pixels so that values will be closer to 0 and 1, so I can divide all the images by 255. So the pixel value will become ranging 0 to 1. This is an additional step. It will not boost the accuracy by a lot because without it as well, I'm getting 90% accuracy. Okay, but you can add this step as well. Then we are reshaping the image to add an extra dimension so that I don't need to add it after every step of because I can directly take this image and I don't need to expand the dimension. I'm doing it here. Then performing one hot encoding, then printing the shapes, then training my very basic neural network model. It's not having any density, not having any CNN layers. The name of the network is ANN model. And then what I'm doing, I'm defining another model which is called as basic CNN. And then I'm training one more model with deeper CNN. Okay. And this has even more parameters. Then what I'm doing, I'm training all the three models with checkpoints. Now, what are these checkpoints? So basically, they will save the weights after every epoch. Okay. Not only that, they will monitor the loss as well. Okay, imagine if I want to train the model for 30 epochs, but the maximum accuracy I have achieved is at model at epoch number 10. After that, the accuracy will start decreasing because you might have already discussed about how training accuracy and testing accuracy and validation accuracy matters. Okay, testing accuracy matters more than training accuracy, and because of overfitting, sometimes the training accuracy will start going down. So in that particular scenario, I can also add these kind of checkpoints that will keep track of loss is decreasing or not. If loss stop decreasing in that particular case, the model will stop the training in that particular step. I don't need to train it for 30 epochs. Even if I mention 30 epochs, the model will stop its training at 10 epochs. Wheresoever it seems like accuracy is not increasing, loss is not decreasing. So this is an additional step that I have added. And then I have started the training process of ANN model. And here you can see ANN.model.fit. This is something that I have also added. In callbacks, I have added early stoppings and model checkpoints so that model will stop early. And after every epoch, the model will save its weight as well. And this is for ANN model. And here I'm saving ANN underscore history. I'm adding this whole thing as ANN history. So ANN history will save this accuracy, this loss as well. Not only training, but testing accuracy as well. So this is what I have done. Then I'm training the second model, then I'm training the third model. And here you can see the model stopped as execution at just 14th epoch because of early stopping. Okay, I have mentioned it for 30 epochs. And here comes the last, which is trained for again 21st epoch, and then the accuracy stopped. And then what I'm doing, I'm saving the weights of all these three models. Okay, because of early stopping, the weights of these models are also saved here. Right now, the notebook is not connected, but if you're executing the whole code, it will save the weights as well. So now I have loaded all the three models, train weight models. I'll also share these weights as well. And then because I'm evaluating these models on the test data, so this will give you training loss, testing loss, and evaluation loss. And then I'm printing the graph. How the accuracy and loss is there for all the three networks. This is important to compare the models, right? So here you can see basic CNN and deeper CNN. From both of them, basic CNN works better because the images are not that detailed. They are very shallow images. I don't need to have 5 convolution layers. Just one will work. But if the images are high quality, then the more the convolution layer, the better the model will become. But definitely deeper CNN is also better than ANN. Okay. And after that, I have built a map. This is called as confusion matrix as well. As the name suggests, it seems confusing. That's why it's called as confusion matrix. But from here, you can see how the image of 0 and the predicted image is 0 as well. So how many times the model predicted the image of 0 correctly? This is correct. But there are 140 times when the image is of 6, but model predicted 0. Okay, so this is for ANN, this is for basic CNN, this is for deeper CNN, so that you can see which images, which classes are not correctly classified. Then I'm going for a side-by-side model comparison for basic graph, like how accuracy is increasing and loss is decreasing. Okay, because I have saved the model history as well. If you look closely, while training the model, I have saved as deeper CNN history. So inside this history, we have everything. After first epoch, what was the accuracy? What was the loss? What was training accuracy, training loss? So this history is something I'm using here. And eventually, I'm also taking a random sample of couple of images, given it to my model and see what my model is predicting. And here you can see this image is of a coat. This image is of a shirt, predicted shirt, but actually a coat. This is a pullover. That means correct prediction. This is predicted pullover and the actual true output is t-shirt. So they are correct and incorrect outputs as well. And as per which particular model? Deeper CNN model. Okay, but you can also modify it as per your own model of your choice. And eventually this is the whole project summary. Now your task, your assignment is to load this data set. This is Cypher 100 dataset. In MNIST, Fashion MNIST, I have just 10 labels. In this, I have 100 labels, 100 different classes. Okay, so in the output neurons, how many output neurons I need to have? How many output neurons I need to have for this? 100. And input neurons, you can check the image. 32 by 32 size. So input neurons, if you are using an ANN based network, that one, if you are a CNN or convolutional layers, so you need to go for different kind of networks. Okay, so your task is to load this data set, train a CNN based network or any network of your choice, and make a proper documentation as I have made. Add checkpoints, okay, save the model for decent epochs, and also take the inference from the model, give it an image and get the prediction out of it. Okay, so make a perfect notebook for this particular data set, and this is your work. Once you have made the notebook perfectly documented, you need to update the notebook on the form that is given to you. Okay, means basically once you have the notebook, download this notebook, upload it on GitHub, and give the GitHub repository link. Not repository link, but exact link. Okay, this exact notebook link, fill it in the form. Okay, don't go here and there. Don't go for Drive and then Collab link. Directly go for GitHub, because in that GitHub you can also showcase this project to anyone. So take these things. Okay, I'm not sure like how the evaluation is done for Harshvardhan sir session. This is how I'm expecting your output to be. You need to create a notebook, make a model that works on this data set, a CNN based model, classification based model, make sure everything is clearly visible, your loss, your accuracy, along with that, the training loss, training accuracy, and all the other kind of things. So all these things should be clearly mentioned, and that's what you need to do. Okay. So that is my expectation from you. And apart from that, if I go to GitHub, this like to get the notebooks and everything. So inside AI projects, I have made a repository, and here 3 hours ago. So these are trained weights of all the three AME models. So you can also download these models, load it on your system, and you can use them anyhow. And you can also go here on this particular link. Does not something like this is something that you should be using, but this is something that will help you. Okay. Now, this notebook, currently this particular notebook, I'm also updating it within 5 minutes. I'll update it on the reference material on the website. So you guys can check it out from there as well. Okay. Will there be reinforcement learning project? No, there will not be reinforcement learning project. Okay. And these important links as well, rest of the links like of Excalidraw and these apps that we have that I have made, and this particular link, all these links I'll update here. Okay, all these reference links I'm updating here on this particular repository. So you can go to this particular notebook and give it a try. So I'm updating all the things here. So there is this Gemini app I'm adding here, and there's another Gemini app. So I'll add all the things in this particular repository. So make sure to give it a check. Clear. So that's it from my side. If you guys have any question, do let me know. I'll wait for like 2 more minutes, and I hope this session makes sense to you. And you guys need to make your own project. Share these project on your on or on GitHub. Make sure to properly document it. That's very important. Documenting these projects are really very important. Okay, because you can get the project pretty easily, but documenting it would be very difficult. Okay, please submit, please explain the submission criteria. Okay, it's just about the project. Don't think of it as I should add this or that. Make sure it's a project properly working, have ANN, have as many features as you can add, have it properly documented. That's it. If your project is working, Even with the bare minimum, you will be qualified. Don't worry about that. How to decide how many layers are required? Okay, that basically depends from where we are coming. So if you are coming from 784 neurons, so shrink it down to 3 to 4 layers will be more than enough. How many neurons are required? That basically depends from how many inputs that I have. How to be the input shape of each layer? What will be the input shape of each layer? Depend upon the output, the input that coming from the layer before that. How to decide a decent batch size? Manipulate the things. Okay, there is no one such number that will do rest of the things for you. Okay, there's no number like 3 layers will work, 4 layers will work, 10 neurons will work. There is no such number. It's called as hyperparameter tuning. You need to tune the things by yourself. Okay, can you please explain the loss function little? Loss function is whenever your model is given an image, so the model will predict something, and there is a predicted output, the actual output. The difference between them is the error for one image. We have 60,000 such images. So the average error is loss. Okay. Average error is loss. And error is actual output and predicted output. Should this notebook be uploaded on GitHub repository? I've already shared the GitHub link, but the same notebook I'm also adding on the reference links. If you want to download the trained models, you can go there. Okay. Can you please explain TensorFlow and Keras? They are just deep learning libraries. Okay, TensorFlow will give you a detailed kind of uh, what I would say way of manipulating the network. Keras is the upper layer of it, where you will not get that much of freedom. What was convolutional layer CNN? It will basically act as feature extraction. Convolutional will help you do feature extraction on images. Submission criteria I've already mentioned. You need to build a model that the way that I have built. That's it. Add as many things that you wanted. If your model is working, you have the data loaded, data pre-processing, build the model, train the model, and added an inference of it as well in getting the prediction, the model will work. That's it. You will be get selected. No, no fancy things. Okay. Share the GitHub link. It's already shared. Thank you so much for joining in, and do give your feedback for the session, probably here or probably on LinkedIn or probably the feedback form that we might share it with you. And that's it. Thank you so much, everyone. And the link I'm adding in the reference in just 5 minutes. Thank you so much. Have a nice day. Bye bye.